So in this video, we're going to look at stepwise selection methods, right? In particular, one of them, and then the next video we do the other one. Right? In the previous one, we did base subset, perfect model, perfect method. But the problem was it was computationally expensive. It was just computationally expensive. Here, let's look at what is called forward stepwise selection method, right? Forward stepwise selection method. It's part of what? Part of this stepwise selection methods, right? Cool. So what we're going to do is we're going to consider a smaller subset of models than the subset selection method that we had previously. This begins with a model with no predictors, and then we add predictors to it. We're going to see how we're going to add the predictors one at a time, and then at each step we are going to look at how our model is changing. So let's look at the steps involved here. What are the steps involved? So step number 1, we are going to start with let M naught be the now model. So it's the model that has no predictors, y equal to beta naught. That is the model with no predictors, right? And then step number 2 is, so for k equal to 0, all the way up to p minus 1, what we are going to do is we are going to consider all the models. We are going to consider all the models that that argument the predictors. So let me write that down there. So first part of step number 2 is we are going to consider all p minus k. We are going to explain this like in the previous video. Key models that augment the predictors in MK with one additional predictor. Cool, with the one additional predictor. What does that mean? Let's see what it means. All right, so we are starting with k equal to 0. So for k equal to 0, so we are saying, right, so let's say our p is equal to 10. Let's say we have our 10 predictors just like previous, right? Consider all 10 minus 0. 10 minus 0, what does that mean? 10. So consider all 10 models that argument predictors in M or K0 in M naught with one additional predictor. So basically what it's saying when it talks about argumenting is basically saying, all right, dude, we are on step number 0, right? K equal to 0. We already have a model. We have a model y is equal to beta naught. So we have y equal to beta naught. That's the model that we have. So consider all 10 that are going to argument this model here that we already have, the M naught model, with one additional predictor. It's basically saying just add one additional predictor to the model that you already have in the previous step. Simple as that. So here it's just saying add one predictor. So here, since we have 10 predictors, we'll be like, okay, so we are going to have 10 models because we're going to say one addition of could be this one. We added x1, or we could have said beta naught, and we could have added x2 instead, or we could have added x3 instead, right? We could have added x3 instead. We could have added x4, x5, x6, x7, x8, x9, x10. So we are adding one additional predictor. So we are going to add we are going to have a total of 10 models. 10 models when we're doing k equal to 0. 10 models, all right? Plus beta 1 x10. So basically, yeah, it's just saying to the model that we had in the previous step, add one additional predictor. Add one additional predictor that you don't have already. Here we didn't have any x, so we what? We added x1, or we added x2, or we added x3, creating our different models like this, right? Creating our different models like that. I hope that part makes sense. And then after we do that, after we've added that one additional predictor, we're still dealing with k equal to 0. We then choose the best model and call it mk plus 1. So in our case, when we're doing k equal to 0, when we're choosing the best model, we know how we're choosing the best model. These models have the same number of variables, so we're going to use RSS. I'm saying RSS squared. We're going to use RSS, or we're going to, let me shut down my heater. We're going to use RSS or R squared. RSS or R squared, right? We choose the best model here. Which one is going to be the best model? This is the best model where we added x3. Cool. And we're going to call it mk plus 1. In that case, we're going to call it, what is our k? K equal to 0. So this becomes our m1. So we have our m1 on the side, right? And then we go back in the for loop. And then the for loop says, okay, now our k is equal to 1. So our k equal to 1. It then says, consider all, what was our p again? Our p was 10. So we're going to consider all 10 minus 1. 9 models now. So consider all 9 models. That argument predictors in mk. What is our k now? M1. So that argument M1. M1 is the model that came from the previous run of the for loop, which is this one here. That's the one that we chose as our M1, right? Remember, we chose this as our M1. So we are going to argument that M1 with one additional predictor. So our X3 has already been taken. So we're going to say for this second step now, for this k equal to 1, this second run of our for loop, we are starting with y is equal to beta naught plus beta 1 x3. And we are going to plus beta, and then we are going to add an additional predictor. We add x1, we create another model where we add x2, another model where we skip x3 because it's already there. We do x4, x5, x6, x7, x8, whatever it is, up to x10. Those are going to be 9 models, right? Let's say and then we choose the best one out of those that we have created in k equal to 1. We choose the best one that we have created. Let's say the best one is going to be when we have added x5. And it says, yeah, when we choose the best, you call it mk plus 1. Our k equal to 1, so it's going to be 1 plus 1, m2. So we are going to call this our m2. And then we go back in the loop. The loop goes back. Now we're doing k equal to 2. Right? K equal to 2. Allow me to write k equal to 2 here. K equal to 2. So it's going to say, consider all p minus k. Our p is 10. 10 minus 2, 8. So consider all 8 models that argument the predictors in M2. Our k is equal to 2, right? K equal to 2. So that argument M2. What is our M2? Our M2 is equal to, this is the one that we said we called M2 because that was the best one in the previous step. So beta naught plus beta 1 x3 plus beta 2 x5. So that argument, this one, let's add an additional, let's create, how many models are we going to create? We're going to create 8 models. In step k equal to 2, we're going to create 8 models by adding an extra predictor here. That extra predictor. So we're going to have a model that is these. One model we have plus beta 1 x1, another model we say plus beta, it's going to be beta 3, let's just say beta 3 x1, someone will be beta 3 x2, another one will be beta 3 x4, or whatever it is. So we're going to do these models. And we choose the best model, and we're going to call it M k plus y. So this is going to be my M3. Whatever best one that we choose. Maybe my M3 from this step is going to be equal to beta naught plus beta 1 x3 plus beta 2 x5. That's the one that we already had. But when we added the additional one and we did the RSS, maybe the best one is going to be this one here. Then we call that M3. And we repeat this process. We repeat this process until we get to p minus 1. So it's going to be 10 minus 1. It's going to be 10 minus 1. So it's going to be until we get to 9. When we get to 9, we would have fit every model. So here we're going to say 10 minus 9, 1. So consider one model at the end. There's going to be one model, and that is with the model where all the predictors are in it. If you want to exercise, just write all the K's with the models that you think are going to be there. These models are easy, are probably easy going to write, because you can guess out, just like I was guessing here. Yeah, I've given M3 to X1. And then for M4 you can give it to another one, X6, whatever it is. You see that when you get to K equal to 9, the K equal to 9th model is the one that has all the predictors. Cool. Then we have done that, right? So we now have our M models. We have this M1 model, and then we have this as M2, and then we have this green one as the M3. Perfect. We have our M. So we are now doing that step again. Step number 3. Select the best of the best. We select the best of the best from our M1. Remember, from our M0, M1, all the way up to our MP model, right? We select the best of the best. And what are we going to use? We're going to use cross-validation error. We can use CP. We can use our AIC. We can use BIC, and we can use our adjusted R-squared. Is our adjusted R-squared. We're going to discuss these very soon. We're going to discuss them very soon. Easy as that. And then we'll say, oh yes, the best model was M1, which was equal to Y1, which is going to, because beta naught, X3. This is the best model. That's what we do. It's the same. It's the same as previous. So if you really were concentrating when you're explaining this, you see that we are no longer doing all the possible models. No, what we are essentially doing is at each step we are adding an additional predictor. Just one additional predictor at each step. One additional predictor to an already existing model. We are not building models from scratch. The best subset was saying, oh, it's K equal to 1. It builds models from scratch. Here we are building onto one we already have. We built onto the null one. This was the null one. And then when K equal to 1, we built on top of it. K equal to 2, we built on top of what we already had. Right? We put on top of what we had. K equal to 2, it was K equal to 1. K equal to 2, we built on top of what we already had. Just by adding one additional predict. So we are not creating models from scratch. We are building on top of what we already have. And that saves us time and computation, because the number of models we'll consider, will be equal to 1 plus the summation of I equal to 0 p minus 1 of p minus k, which is just basically equal to 1 plus, if you have done an arithmetic series, you see that this is the summation. It's going to be like that, because this is a simple arithmetic series, right? So it's going to be like that. So that's how you calculate how many models you are going to do. So in our case, when we did best subset, right? Best subset was looking at 2 to the power of p models. It was going to build 2 to the power of p models. So when our p was equal to 20, we're doing 2 to the power of 20, which was approximately equal to 1,048 576. I think it's actually equal to 1 million. 1 million models like this. 1 million and 48,576 thousand models. Right? 48,576 models like that. Right? 1 million and 48,576 models. Right? And then when we are doing forward, but in our forward subset, forward stepwise selection method, what is going to happen is this. We are going to do 1 plus, instead of p, we put out 20 plus 1 divided by 2, right? Divided by 2. So this is just going to be 10. 20 plus 1 is going to be 210. 210 plus 1, 211 models. So we are considering 211 models. Compare the two. How insanely different is that number? From 1 million to 211, right? So forward stepwise method brings it down to 211 models, right? So we might be like, yes, this is brilliant. It's computationally advantageous and stuff like that. So it is brilliant. The problem is stepwise model, this forward stepwise model, it is not guaranteed to give you the best model. It is not guaranteed to do that. The reason is because, let's just do a quick example so we can see why. So for example, imagine we had p equal to 3 predictors, right? We have p equal to 3 predictors, right? So if when we start our k equal to 1, when we're adding, we obviously start with y equal to beta naught. But when we have k equal to 1, let's imagine the 1 that we add to this when we are starting. When k equal to 0, I mean that k equal to 0, when we are adding the 1, imagine our model is going to be like this. The one that we add, imagine it's the x1 that is the best one. That is the best one to add at that moment. This becomes our m1. Imagine this becomes our m1, right? And then, so this is the one variable model. This is the one variable model. So imagine the best 2 variable model ever. The best 2 variable model in our case. If the best 2 variable model, imagine it was it is this one here. It is the one that is x2 and x3. It is the one that is x2 and x3. The problem with our forward, the problem with our forward stepwise subset selection method is when you are building your 2 variable model, your M2, you are going to build it on top of what you already have. So which means the best that is going to be the needs to have an X1. It has to, because we're building on top of it. It just has to have the X1. That is the principle of what? Of forward stepwise. We build on what we already have. So that becomes a problem, because we know that in the real world, this is the best. The best is the one that is x2 and x1. But we are forced to forego, or with forward stepwise, we won't even see it, because we are going to build on top of this nonsense x1. And then we might say, oh yes, this is the best model. Building on top of our x1, this might become the next best model. But in the real world, this is the ultimate best. So we have missed the ultimate best because we had to build on top of x1, which was nonsense. It was good when we had 1 variable. But then when we have 2 variables, it stops being the best. The x1 part stops being the best. It stops giving us information that we need. We need x2 and x3 together. That will give us the best information, the best model. But if forward stepwise forces us to build on top of x1 that we already had. And when you do that, when you run the credit data, set, that's something that you are going to see. So number of variables. What you're going to see is number of variables. These are the models that you can create. So number of variables 1. So when you have 1 variable, here let's just put our best subset. When we run best subset, and here when we run forward stepwise. Let me try draw a straight line. Cool. And then here, let me try draw a straight line. It's not straight. I'm trying. But yeah, cool. So when we have one variable, the best one is going to be the best one to predict whether someone's going to default or not in the credit data set. In the credit data set that we have, in the credit data set, the one that is going to predict default status is going to be rating. When you're running best subset, it's going to say, oh, you want for one variable it's rating. Choose rating. Rating is the best one. So what I mean is, yeah, it's a subset of the variables. So the variable rating will be the best one. When you do forward stepwise will say yes, rating is the best one. Cool. That is when we have one variable. When we have two variables, which one is going to be the best? It's going to tell you that the best subset is going to say the one that is rating and income. So this is the best subset, rating and income. For forward stepwise, it is rating and income. Because forward subset, it builds on top of what we already have, right? It builds on top of what we already have. So it built and it added income as the one that will create the best M2. Cool, right? And then when you have three variables, best subset will say rating, income, and student. This is the subset that you need to consider when you're doing a model with three variables. And then forward will say, of course, it will say rating, income. It has to do that because it's building on top of those. And then it's going to add student. So far so good, right? So far so good. And then when we have M4, for four variables, best subset, it builds models from scratch and then compares them. So here it built models for all one variable models and compared them, and it chose the one with the rating. For 2, it built all possible ones with 2, and then it compared them, and then it said the model that is rating and income, that's the best model. Forward stepwise said, okay, for my one, on top of my beta naught, I want a model that is beta 1 times rating. That is the best one for 1. And then for number 2, it's going to say, okay, I already have rating. I'm going to add income. But for best subset, it said from scratch, all possible ones with 2 variables. And then it chose those ones. And then for variable number 3, best that have 3 variables. All of them, any combination I can come up with 3 variables. Which one is going to be the best of those? And then it came up with this. For forward, it said, I already have 2. So if I add another variable, which one is going to be the best variable to add? And then it added student. So for best subset, when we have 4 variables, it's going to look at all possible models that can be created using 4 variables. And it's going to tell you that the best one is going to have the number of cards the person has, the income the person has, the student status, the person a student or not, and what is their limit. What is their limit, their credit card limit. That is the best combination of 4 variables for best subset. But forward stepwise does what? It adds on top of that. It says, I already have these. So when I add the 4th variable, I'm going to add all the other ones that are left, and I'll just choose the result and the best resultant out of the addition of the 4th one. And then it's going to say the one that will give you the best will be when you add limit. See how different these models are. Best subset, we said this is the best one. It's computationally expensive, but it is the best because at each stage it gives you the ultimate best for each step. So for the 4th step, this is the ultimate best combination of cards, income, student, and limit. But then forward stepwise, since it builds on top of things that we already had, rating stopped being useful. On the 4th, in the 4th, when you're doing 4 variable, rating stopped being useful. Best subset is already telling us that rating is not useful, but we are keeping it because we had to build on top of it, which sucks because we have missed the best model. We have missed the best model here. Rating is useless, right? Rating is completely useless. It's being replaced by cards, but we have missed that one because we haven't done it. Maybe when we go to 5, the 5th model, maybe card will then be added, but we are carrying we're carrying a nonsense variable there. So that is just that is the problem with forward stepwise. Advantage with forward stepwise though is forward stepwise it can always be applied. It can always be applied even when n is less than p. It will be applied to a point up to when n equal to p. That's only when you can apply. I think yeah, you cannot apply it. I think I'll put an annotation to this. But I think forward selection, it can always be applied. Oh yeah, you can always apply it for m. So it's going to be m0 all the way up to mn minus 1. So you cannot apply it to m equal to p. So you can always apply it to mn minus 1. So you can get it to these steps because you can still fit your least squares. You can still fit your least squares like that. You can still fit your least squares, right? But you will not yield. But least squares breaks down now when you're yeah, it'll break down now when you're thinking. I think I'm making a mistake. There's a part. I think I made a mistake in my notes here. I'll put an annotation on the video to explain this last part here. But forward selection will always. Stepwise selection will always be can be applied. I mean, it can be applied even in cases where there are higher dimensions, where your n is less than p. You can apply it, but I'll explain up to what limit. I'll put that as an annotation. But so far we've done forward selection. I hope you understand what forward stepwise selection method is. It's just this. That's what it is. Add an additional variable at each step. When you add different additional variables, right, you choose which one is going to be the best addition. And that's going to be your M1, your M2, your M3, your M4, and stuff like that. But the disadvantage is just that the chances are high that you miss the best model. You're going to miss the best model. So cool. This was forward stepwise selection. In the next video, we're going to do backward stepwise selection method.